Hello, this is Dr. Gardner. We're going to be talking about Chapter 6 today, involving quantities and chemical reactions. When we're talking about quantities and chemical reactions, we're going to be looking at what we call stoichiometry. I will define this in greater detail in just the next slide. But first of all, before we get started, what we're going to be doing in this specific discussion is looking at how to build skills for doing stoichiometry calculations by looking at an analogy to putting together a turkey sandwich. So we're going to look at building a turkey sandwich as if it were a chemical reaction, even though it is not. So we'll be able to use stoichiometric relationships in our turkey sandwich equation to relate to how many sandwiches we can make with respect to the ingredients we have to make the sandwich. We'll relate this to how many slices of bread or lettuce we might use, or different components of the sandwich. And we'll use this analogy to help you understand other chemical reactions as we continue on in this chapter. We'll also compare how to use the masses of a reactant or a product to compare to the quantities of what we're using by looking at the grams per slice of bread, or per piece of lettuce, or per slice of cheese with respect to our analogy. We'll see later how we can relate that to using molar masses to convert from grams to number of moles of a substance we might be looking at. Now, first of all, when we consider stoichiometry is just a quantitative way, meaning a method that uses measured numbers to find the amount of a reactant or a product and compare that to any other reactant or product in a chemical reaction. And so if we look to the original meaning of stoichiometry, its Greek meaning literally translates to the measure of elements, and that's exactly what we'll be doing. We'll be measuring the quantity of atoms or ions or molecules in a chemical reaction by doing stoichiometry calculations in this chapter. So first of all, if I'm going to do a stoichiometry calculation, we need to understand how to balance chemical reactions, and I need to have a correctly balanced chemical reaction in order to do my stoichiometry correctly. What we're going to be doing once we have a balanced chemical reaction is we're actually looking at the law of conservation of mass. We're ensuring that we have the same number of atoms of every element in the reactant side of a chemical reaction as compared to the product side of a chemical reaction. Once I have the correct coefficient, which is the number in front of each atom, ion, or molecule or formula unit in my chemical reaction, I can look at that number in the front of each formula unit in this case for my lead 4 hydroxide reacting with sulfuric acid to form lead 4 sulfate and 4 water molecules. In this case, the numbers in front indicate the number of formula units that we are using, or the number of moles for molar ratios. So really these coefficients, we might call them stoichiometric coefficients. Sometimes I refer to them as mole ratios or stoichiometric ratios when I compare these coefficients to one another. So for example, when I'm reading this reaction, I could say that any coefficient that's not shown is a 1. So I have 1 mole of lead 4 hydroxide reacts with 2 moles of sulfuric acid to yield or produce products of 1 mole of lead 4 sulfate and 4 moles of water. So the molar ratios, or the stoichiometric ratios, would be comparing these relationships. So I could say for every 1 mole of the lead 4 hydroxide that reacts, I must be also using 2 moles of sulfuric acid. That 1:2 ratio is my molar ratio, or my stoichiometric ratio. Or if I said for every 2 moles of my sulfuric acid that reacts, I'm producing 4 moles of water in this chemical reaction, that would also be a stoichiometric ratio or a molar ratio. So I can compare any of these coefficients to any of the other coefficients to relate mole quantities of one reactant to another reactant or product, or one product to another product or reactant. I can compare any of them and use these ratios for calculations. So when I'm setting up a stoichiometric calculation to compare the amounts of, let's say, reactants and products, the very first step you want to take is write a correctly balanced chemical equation. So if you don't remember how to balance chemical reactions, you will want to go back and review that, because you will need a correctly balanced chemical reaction in order to have the correct stoichiometric coefficients. Now, once you have the correct balanced chemical equation, we may start with the quantity of a substance. Let's say maybe it's in grams. I might have to be able to use a molar mass to convert from grams to moles. So my original calculations where I learned how to convert from grams to moles or moles to grams using molar masses, I'm going to be doing those types of calculations here again in this chapter. So once I can convert from the amount of a substance to its number of moles, we can relate that to the balanced equation. We look at the coefficients in my balanced equation. My stoichiometric ratios or molar ratios can be found by comparing one coefficient to another coefficient in the balanced reaction. Once I do that, I can calculate the number of moles of the sought quantity of either another reactant or a product. Now, once I convert from my moles of my original substance to the moles of the second substance in the chemical reaction that I'm looking at, I can go ahead and convert those moles to any unit I might be interested in. So if I have the moles of, let's say, a product, and I want to convert back to grams, I can use the molar mass of that product. So I have to use the molar mass of the second substance I'm looking at. We'll be working on some examples of this so you can see how to apply these steps. First of all, if I want to list kind of the steps I'm going through, let's say I had the mass of a reactant. I could convert from the mass of the reactant into moles of reactant by using my molar mass. So if I take the grams of the reactant, divide by the molar mass of the reactant based on calculating the molar mass from its formula, I could then convert to moles of that reactant. Once I'm converting to moles of a reactant, that's when I'm really doing the new type of calculation that we're applying in this chapter, where I'm finding a stoichiometric ratio from the balanced equation. So if I want to convert from moles of reactant to moles of product, what I will do is look at the balanced equation, and the molar ratio will be found from how many moles of that reactant must be reacting to form how many moles of product from those coefficients that I look at. So we'll be applying that with our analogy today with the turkey sandwich, and then we'll be applying that to chemical reactions in the next discussion. Once I have the moles of product, I may be asked to convert from moles of product into, let's say, grams of product. If I want to convert from moles to the mass of the product in grams, well, then we would multiply by the molar mass based on the formula of the product. So make sure you're using the correct molar masses for either the reactant or the product that you're looking at when you do those conversions. So that's kind of the steps I'm thinking about when I set up these types of calculations. Now, if I have a calculation where I begin with being given a mole quantity, well, then I can merely convert from moles to moles with a molar ratio. So there are occasions where I may not have to convert from grams to moles first, or from moles back to grams, but I should be able to do so if I'm asked to do that. So let's look at our analogy of the turkey sandwich here. So let's say we're going to prepare the best turkey sandwich we can, and maybe we're going to open our own sandwich shop up. And so the perfect turkey sandwich that I want to sell must be composed in the following manner. I want to make the turkey sandwich by using 2 slices of my bread, 1 slice of turkey breast, 1 slice of your favorite cheese, 2 pieces of lettuce, 3 slices of tomato. Okay, now if I pretend this were a chemical reaction, which it is not, we can maybe write an equation that might look something like this. We could say that 2 slices of bread would react with 1 slice of turkey to form, and react with 1 slice of cheese and 2 pieces of lettuce and 3 slices of tomato to yield or produce a product of 1 sandwich. So I've written coefficients in front of each of the ingredients and my product to indicate how many of everything I'm looking at. Now, this isn't quite the same as my molar ratios, because I'm not dealing with mole quantities of these slices of turkey or bread, or mole quantities of sandwiches. That would be a huge quantity with Avogadro's number, right? So we're looking at more a ratio that's a slice ratio, or a slice to sandwich ratio, but it's very similar to what we would do with a chemical reaction. So if I wanted to say my ratios here, I could say 2 slices of bread would be used for every 1 sandwich that we produce, or I could say 3 slices of tomato are being used for every 1 sandwich that we produce. When I look at these coefficients in a chemical reaction, though, we'll see that later that we can relate that to mole quantities very readily, but we'll set up the calculations in a very similar manner to what we're doing today. Now, if I was interested in converting from gram quantities to mole quantities, we would use molar masses. In a deli, we might be relating gram quantities to slices that I'm cutting of my different materials. So let's say that we're given some information information. We're told that one slice of bread on average weighs 65.5 grams to make our sandwich. One slice of deli turkey would be 56.7 grams based on how thick we're slicing the turkey and the type of turkey we're slicing. One slice of cheese for the type of cheese we picked was 28.3 grams per slice. One piece of lettuce was 10 grams, and one slice of tomato was 12 grams, and the entire sandwich, when we put together, the sandwich weighs 272 grams. So now we have a gram to slice or gram to sandwich relationship, a little bit like our molar mass grams to mole relationships. So we'll be using these relationships in calculations very similar to stoichiometry reactions. So let's start with our first reaction. I have rewritten here the equation for producing our turkey sandwich. I've also marked here in red the important coefficients that I'm going to use for the following calculation. So if I have 5 slices of turkey, and I would like to know how many turkey sandwiches I can make, assuming we have an excess, meaning more than enough of all the other ingredients to make however many sandwiches we might be interested in. So I'm worried about my limiting ingredient. Sometimes we'll call that a limiting reactant, being the turkey. We're going to run out of the turkey after we use the first 5 slices. If that's the case, let's decide how many sandwiches we can make if the turkey runs out first before anything else. So in this case, if I had 5 slices of deli turkey that I was using, I can set up a calculation using dimensional analysis where I use a molar ratio. Well, in this case, it's actually my slice to sandwich ratio from the coefficients. So if I look at my coefficients, I have, for one slice of turkey, I'm producing 1 sandwich. So if I set up that ratio here in my dimensional analysis, I say, well, I divide by 1 slice of turkey to cancel my units of slices of turkey, and I'm going to multiply by 1 sandwich being produced. So it's just a 1-to-1 ratio here, but I still like to write it down so I don't forget to look at the ratios for when it isn't 1-to-1. So this is really the heart of a stoichiometry problem, looking at these coefficients and relating the ratio between the 2 coefficients. That's the heart of a stoichiometry problem. In this case, since it only takes 1 slice of turkey for every sandwich that we produce, I can produce a maximum of 5 sandwiches, assuming I have plenty of all the other ingredients that we were making sandwiches out of. Now that seemed pretty straightforward, and most of the time you probably wouldn't bother to write this down. But when we get to more complex problems, it will be very useful to write down these steps and think about them logically. So let's try another problem. Let's say I'm interested in how many sandwiches I can make if my lettuce is going to run out first. So I have 13 slices of lettuce left, plenty of all the other ingredients, but I'd like to know how many turkey sandwiches I can make maximum by the time I run out of lettuce. So if I have 13 slices of lettuce, then I can look at the stoichiometric ratio for my coefficients of 2 slices of lettuce for every 1 sandwich to predict how many sandwiches I could make. So I'm going to divide by the slices of lettuce. So 2 slices of lettuce in my coefficient here. So I take 13 slices of lettuce that I had to begin with, but it takes 2 slices of lettuce for every 1 sandwich that we produce. So I have a 1-to-2 ratio that I'm using for my stoichiometric ratio. So I look at my coefficients to produce this ratio from the coefficients, which when we deal with moles instead of slices and sandwiches would be a molar ratio. Right now I'm just going to call it a stoichiometric ratio, which is another term we can use for that ratio. So if I take 13 divided by 2 and multiply by 1, we find we can make 6.5 sandwiches in this case. So the maximum number of sandwiches I can make that are the perfect turkey sandwiches with the correct ratio of all the ingredients would only be 6.5 sandwiches. At that point, I run out of lettuce before I run out of anything else, we're assuming. So it's very useful to relate these stoichiometric ratios to one another to predict quantities of, let's say, a reactant compared to quantities of a product. I could relate these quantities of one reactant to another reactant as well, though. Okay. Let's try working this type of calculation backwards. Let's say we're told we want to be able to make 13.5 sandwiches, and I'd like to predict how many slices of tomato that I might want to cut. And you probably do these types of predictions in your home all the time when you're putting together sandwiches. You might decide out of all of your ingredients, what are you worried that you'll run out of first? And if you're getting ready maybe for family or company to come by, you might want to make several sandwiches, and you might want to predict how many tomato slices to cut up to prepare for your sandwich. sandwiches for your guests? Well, in this case, we know we want 13.5 sandwiches. Perhaps we only want a half a sandwich for somebody with very little appetite. And so in this case, the 13.5 sandwiches can still use a stoichiometric ratio, but I need to divide by sandwiches this time instead of by tomato slices. So I know that for every one sandwich, we will need 3 slices of tomato. So I have a 3-to-1 ratio now for my stoichiometric ratio. My stoichiometric ratio is from the coefficients from the balanced equation again. So I can go ahead then and divide by 1 and multiply by 3, and I find I would need 40.5 slices of tomato to make 13.5 sandwiches, 13.5 sandwiches. So we can use these stoichiometric ratios very easily to figure out quantities of any reactant compared to any other reactant or product. In this case, I compared a product back to the quantity of reactants. Now, if I would like to know if I had 16.5 slices of tomato, how many pieces of bread I might use, I can compare one reactant to another reactant. I don't always have to compare reactants to products. So I can compare any of these stoichiometric ratios to any other stoichiometric ratio in the reaction. So here's comparing reactants to reactants. So if I have 16.5 slices of tomato, I know in my stoichiometric ratio I want to divide by slices of tomato to cancel units. So I'm going to say, oh well, I look at my balanced equation, it has a 3 for the coefficient. So I'm going to put 3 slices of tomato in the denominator for my stoichiometric ratio. And when I look at my balanced equation to relate to bread, the coefficient's a 2, so I multiply by 2 slices of bread. Now my slices of tomato will cancel units, and I'll end up with slices of bread. So I take 16.5 times 2 divided by 3. That's my stoichiometric ratio, this 2-to-3 ratio from those coefficients. We end up seeing that it would require 11 slices of bread to react with 16.5 slices of tomatoes to produce my sandwiches. Okay, so I can compare reactants to reactants in this case. Now, in all of these cases, we're beginning with slices of tomato or slices of bread or number of sandwiches, and we didn't have to deal with any gram quantities. So let's say now that maybe we had gram quantities given for the amount of some of our ingredients or products and compare that to our stoichiometric ratios. This would be similar to having gram quantities and having to use a molar mass to convert to moles. In this case, we're going to convert from grams to number of slices or numbers of sandwiches. Okay, so remember I have the mass of my slices of different ingredients compared to the sandwich and its mass. So let's say I was told that I would like to know how many sandwiches I can make if somebody has weighed out 393 grams of my bread. And I'm going to go ahead and slice my bread, so the thickness of bread is 65.5 grams per slice of bread. Now, since I have a gram quantity, I'm going to use this relationship, which is a little bit like a molar mass. It's more of a slice mass in this case. And what I'll do is divide by my slice mass to come up with my slices of bread. So 393 grams of bread, if I divide by 65.5 grams of bread for every one slice, which I was given here and I've underlined, then I can find out how many slices of bread that I had. It would give me 6 slices of bread. 393 divided by 65.5 is 6 slices of bread. Now, once I have slices of bread, I can use my stoichiometric ratios. So I can go ahead and look at the ratios of slices of bread to numbers of sandwiches. So I can say for every 2 slices of bread, I want the slice of bread in the denominator to cancel units here. I can produce 1 sandwich. So my stoichiometric ratio wasn't until the second step here. I had to convert from grams to slices. For a chemical reaction, I would convert from grams to moles using a molar mass. Once I get to moles, or in this case, once I get to slices, I can use my stoichiometric ratio from the balanced equation, from the coefficients of the 2 substances I'm looking at, to relate to the quantity, in this case, of product I can form. So I take the 6 slices of bread divided by 2, gives me a maximum of 3 sandwiches I can produce with this mass in grams of bread. So just remember, if I'm given gram quantities, I want to get to slices in this case, or for a chemical reaction, I'll convert from grams to moles by dividing by a molar mass. So that's what I'll be doing later. So let's look at a similar calculation. I'd like to know how many sandwiches I can make if I have 180 grams of tomatoes. So if I have 180 grams of tomatoes and I look up the slice mass, this would be like looking up molar masses using our periodic table. Here I have a table of the masses per slice. So I have 12 slices, or sorry, 12 grams, I mean to say, for every one slice of tomato. So I have 180 grams of tomato. Let's see how many slices we have. And then let's use the stoichiometric ratio from the coefficients to calculate how many sandwiches I can produce. So I have 180 grams of tomato. I divide by 12 grams for every slice of tomato to find out how many slices of tomato I have. I have 15 slices of tomato if I have 180 grams. The only difference here to a chemical reaction is I calculate the moles of a reactant rather than the slices of tomato if I was doing this for a chemical reaction. So I would divide by the molar mass instead. Once I know my slices of tomato, or once I get to mole quantities, I can look at my stoichiometric ratio. I can say for every 3 slices of tomato here, we can produce 1 sandwich. So I want to cancel slices of tomato, so I divide by tomato slices. And so 3 slices of tomato will produce 1 sandwich, so I'll have the number of sandwiches. That's my stoichiometric ratio here that I put the heart around. That's the heart of my stoichiometry problem. Okay. That tells me that I could produce 5 sandwiches out of 180 grams of tomato. Okay, so that's a pretty useful set of calculations that we'll be using again later. Now, so far we've been taking grams of a reactant, or grams of an ingredient in this case, and finding the number of sandwiches we can produce. But we can work these problems the other direction as well. Let's say I'm told that I have 952 grams of sandwiches in a container, and I'd like to know how many slices of lettuce you would have had to use to produce that number of sandwiches. So now I have grams of the product. So I'm going to go ahead and I could use a molar mass of the product and divide by the molar mass to get to moles if it was a chemical reaction. In this case, I'm using a sandwich mass. So there's 272 grams for every 1 sandwich. So I take 952 grams of sandwiches. I divide by 272 grams of sandwiches for every 1 sandwich that was produced. That will determine how many sandwiches I began with, which was 3.5 sandwiches. Right? If I take 952 divided by 272, it tells me I had 3.5 sandwiches that I began with. Now the next step, once I get to number of sandwiches, in a chemical reaction this would be once I got to number of moles of a product, I could go ahead and use the molar ratio, or in this case the stoichiometric ratio from the balanced equation. So I have 1 sandwich for every 2 slices of lettuce. So I divide by 1 sandwich for every 2 slices of lettuce to predict how many slices of lettuce had to be used to produce the 3.5 sandwiches. That's the heart of my stoichiometry problem that I'm getting from these stoichiometric coefficients, the 2 and the 1. So if I go ahead and multiply by 2, that tells me I would have had to have used 7 slices of lettuce to produce the 3.5 sandwiches, which would weigh a total of 952 grams. Okay, so these could be very useful calculations to use if you were working in a business where you wanted to look at the quantity in grams of your product you would be shipping, let's say. So this could be very useful there. Let's do a similar calculation now where I'd like to go to all the way to grams of lettuce. So let's say we had to do this calculation instead of stopping at slices of lettuce. I'd like to know how many grams of lettuce that I have. So realize I can convert back to grams by using, in a chemical reaction, the molar mass of the other substance I'm looking at. So I could use a molar mass for a reactant here. In this case, I'm going to use a slice mass. So I set up the same type of calculation. I want to know if I had 952 grams of sandwiches, how many grams of lettuce should you use? This could help you predict how many grams of lettuce to order, for example, for your business. But probably on a much larger scale in that case. So I have 952 grams of sandwiches. We already calculated that if it was 952 grams of sandwiches, there was 272 grams for every 1 sandwich. So we'd already calculated that was 3.5 sandwiches. So we've already done the first part of this calculation. Once I get to number of sandwiches, we used our stoichiometric ratio from the coefficients again to calculate 7 slices of lettuce. But I didn't stop there. So I'm adding in an additional step. Now we want to go ahead and find out how many grams of lettuce you use per slice. So 1 slice of lettuce is 10 grams. So if I multiply by my slice mass here, 1 slice of lettuce is 10 grams. If I multiply by that, that would give me 70 grams of lettuce should be used. Okay, and this would be similar to a chemical reaction. Instead of sandwich masses or slice masses, we'd use molar masses. So let's think about this. If this was a chemical reaction where these are mole quantities, we take the grams of sandwiches, we divide by its molar mass to get to moles of sandwiches if it was a chemical reaction. Then I'd relate 1 mole of the product to 2 moles of the reactant, and then I would calculate the molar mass of the reactant, which I would multiply by the molar mass of the reactant to calculate the grams of the reactant. Okay, so that would be the only way this would be different, but it's a very similar type of calculation. Now, if I would like to compare, let's say, the grams of turkey that should be used to the grams of bread that I should use, so here I'm relating gram quantities of turkey to the gram quantities of bread that I should use. I'm just pointing out that you can relate quantities with stoichiometric relationships of 2 reactants in this case. It doesn't have to have the product involved in the calculation. So in this case, I'm interested in using 302.4 grams of turkey to produce my sandwiches, but I'd like to know how much bread to use in grams. So I need to convert from grams of turkey to my slices of turkey. In a chemical reaction, I would convert from grams to moles, though. That's the only difference. So I go ahead and look at my turkey slice mass, which is 56.7 grams of turkey for every 1 slice of turkey. Okay, that would tell me that I would be using 5.33 slices of turkey at this point. Now, once I get to slices of turkey, I can use my stoichiometric ratio, which is going to be 1 slice of turkey for every 2 slices of bread. So I'm dividing by 1 slice of turkey to cancel my units out for every 2 slices of bread that I should use. So I calculate there with the heart of my stoichiometry problem with my stoichiometric ratio that I should be using 10.7 slices of bread. Once I have my slices of bread, we convert to grams of bread by looking up the bread slice mass. This would be for a chemical reaction. I'd look up a molar mass. I'd calculate the molar mass. So for my slices of bread, you notice I have 65.5 grams of bread for every 1 slice. So I multiply by the slice mass. If this was a chemical reaction, I'd multiply by the molar mass. So I take 65.5 grams of bread times the 10.7 slices, and I'd find that I'd have to use 6.99 grams of bread with the 302.4 grams of turkey to relate the quantities correctly here with the stoichiometry. Okay, so that really will prepare you well for our first set of calculations using chemical reactions, which will be in our next tutorial. So hopefully this will be a nice example because we can all visualize easily how to produce turkey sandwiches. Okay, so I hope this was helpful. The next tutorial will be looking at actual chemical reactions, but applying the same techniques with our molar ratios or our stoichiometric ratios from the balanced equations to calculate quantities of reactants compared to other reactants or products in our chemical reactions. Thank you very much.